What if everything you thought you knew about reality was just the tip of the iceberg? Picture this, a hidden layer of the universe where particles blink in and out of existence, where matter defies logic by being in two places at once, and where the very act of observing something changes its behavior. This isn't science fiction, it's the wild, wondrous world of quantum mechanics, and it's more bizarre than anything our everyday experiences could prepare us for. Today, we're pulling back the curtain on the universe's best-kept secrets with 28 quantum quirks, those mind-bending phenomena that rewrite the rules of physics as we know them. Think about the solid ground beneath your feet, the predictable arc of a thrown ball, the steady glow of a light bulb. All of it feels reassuringly normal. But dive down to the subatomic level, and that certainty vanishes. Here, particles communicate instantaneously across vast distances, as if space and time don't apply to them. Here, a single electron can act like both a particle and a wave, depending on how you look at it. It's a realm where the impossible isn't just possible, it's everyday behavior. And the craziest part, these quantum quirks aren't abstract ideas confined to lab experiments. They're the invisible scaffolding holding reality together, shaping everything from the stars above us to the devices in our hands. So why does any of this matter to you? Because quantum mechanics isn't just for physicists in white lab coats. It's the foundation of technologies like smartphones, MRI machines, and even the internet. Beyond that, it challenges us to rethink what's real, what's possible, and how deeply interconnected the universe truly is. Over the next 28 revelations, we'll unravel the mysteries of quantum entanglement, peer into the paradox of Schrödinger's cat, and explore how particles tunnel through barriers like ghosts passing through walls. Each quirk is a piece of a puzzle, one that reveals a cosmos far stranger, far more beautiful than we ever imagined. Buckle up, because by the end of this journey, nothing will look quite the same. The quantum world is calling, and it's time to answer. Let's start with the first quantum quirk, and it's a big one: superposition, the mind-bending ability of particles to exist in multiple states at once. You've probably heard of Schrödinger's cat, that poor feline stuck in a box being both alive and dead until someone checks on it. While the cat itself is just a thought experiment, the principle it illustrates is very real. At the subatomic level, particles like electrons don't commit to a single position or state until they're measured. Before observation, they're in a fuzzy cloud of possibilities, a blend of all potential outcomes. This isn't just some abstract idea confined to textbooks. Quantum computers harness superposition to solve problems that would take traditional computers centuries. Instead of processing information in binary, ones and zeros, quantum bits or qubits can be both 1 and 0 simultaneously. That means they explore countless solutions at the same time, unlocking unprecedented computing power. Think of it like flipping a coin. Classical physics says it's either heads or tails when it lands, but quantum mechanics lets it stay spinning mid-air, embodying both outcomes until you catch it. But superposition isn't just about computing. It forces us to confront deep questions about reality itself. If particles only choose a state when observed, does that mean the universe is fundamentally uncertain until we interact with it? Some interpretations suggest that reality is a tapestry of probabilities, solidifying only when measured. Others argue that every possible outcome spawns its own parallel universe. Whether you find it thrilling or unsettling, one thing's clear: superposition shatters our everyday intuition about how the world works. And here's the wild part: we've seen it in action. Experiments like the double-slit test show particles behaving as waves, spreading out in multiple paths until observed, at which point they collapse into a single location. It's as if the universe itself hesitates until we look, playing out all options until forced to pick one. This isn't just physics, it's philosophy, blurring the line between the observer and the observed. So next time you flip a switch or check your phone, remember, underneath it all, the quantum world is still spinning, undecided and utterly mysterious. Just when you thought superposition was strange enough, the quantum world throws another curveball: wave-particle duality. Imagine light acting like a wave one moment, spreading out in ripples like water in a pond, and the next moment behaving like a stream of tiny, bullet-like particles. This isn't some theoretical guess, it's a fundamental property of nature, first revealed in one of the most famous experiments in physics, the double-slit test. Shine light through two narrow slits, and if no one's watching, it creates an interference pattern on the other side, those alternating bands of light and dark that only waves can produce. But the moment you set up detectors to see which slit each photon goes through, the pattern vanishes. The light suddenly acts like particles, hitting the screen in precise points, as if it knew it was being watched. This isn't just about light, either. Electrons, protons, even whole molecules have been caught in the act, switching between wave-like and particle-like behavior depending on whether they're being observed. It's as if the universe has a built-in stage fright. Everything performs one way when unseen, then abruptly changes its act under scrutiny. Think of it like a musician playing a haunting melody when no one's listening, but the second an audience appears, they switch to playing individual notes. The question is, why? Why does reality seem to change its rules based on whether we're paying attention? Some of the most cutting-edge technologies rely on this very quirk. Electron microscopes, for instance, use the wave nature of particles to see objects too small for light to capture. Meanwhile, solar panels harness the particle-like behavior of light, with photons knocking electrons loose to generate electricity. Even the screens we stare at every day depend on this duality. LEDs emit light because of electrons transitioning between energy levels, a process that blends both wave and particle concepts. But the implications go far beyond gadgets. Wave-particle duality forces us to confront the limits of our intuition. In the macroscopic world, things are either waves or particles. Ocean waves don't suddenly turn into marbles when you look at them. Yet at the quantum level, the distinction blurs entirely. It's not that particles are sometimes waves and sometimes particles. They're fundamentally both, all the time, their true nature only revealing itself in how we choose to interrogate them. This challenges the very idea of an objective reality independent of observation. Are we uncovering how the universe works, or are we, in some way, participating in its creation? The mystery deepens when you consider that this duality isn't limited to tiny particles. In recent years, experiments with large molecules, even ones made of hundreds of atoms, have shown wave-like interference. The boundary between the quantum and classical worlds is fuzzier than we ever imagined. Maybe, given the right conditions, even objects on human scales could exhibit this split personality. Imagine a future where baseballs or coffee cups could, under extreme precision, create interference patterns. It sounds absurd, but quantum mechanics has a habit of turning absurdities into undeniable truths. So the next time you switch on a lamp or glance at your phone, take a second to marvel at the light itself. Those photons flooding your room aren't just particles or waves, they're both and neither, defying categorization in a way that still baffles the brightest minds. Wave-particle duality isn't just a quirk, it's a reminder that the universe operates on rules far stranger, far more flexible than our everyday experiences suggest. And this is only the second stop on our journey. Just wait until you see what comes next. If superposition and wave-particle duality left you questioning reality, quantum entanglement is where things get truly mind-blowing. Picture two particles born from the same event, their fates forever intertwined. Now separate them by thousands of miles, even light years. And here's the kicker. Measuring one instantly determines the state of the other, as if space and time don't exist between them. Einstein dismissed this as spooky action at a distance, convinced it violated relativity's cosmic speed limit. But decades of experiments, from lab benches to satellite tests, have proven entanglement isn't just real, it's one of the universe's most fundamental features. Take the famous Bell test experiments. Scientists sent entangled photons to detectors far apart, measuring their properties at the exact same moment. Classically, the results should align only if information traveled between them, which would break light-speed rules. Yet time and again, the particles matched perfectly, as if they'd never been separated. It's like having a pair of magic dice. Roll one in New York and the other in Tokyo, and they'd always land on identical numbers, defying all odds. This isn't just weird physics, it's a crack in our understanding of locality, the idea that objects need a medium or signal to influence each other. So how does this spookiness work? One explanation is that entangled particles don't have independent states at all. Instead, they exist as a single quantum system, described by one shared wave function. Measuring one particle doesn't send a signal to its partner. It simply reveals a property that was always correlated, like two sides of the same coin. But here's where it gets wild. Those properties aren't predetermined. Until measurement, both particles exist in a superposition of all possible states, and the act of observing one collapses the entire system instantaneously. This isn't just theoretical gymnastics. Quantum teleportation, yes, that's a real term, uses entanglement to transmit information across vast distances without physical travel. Imagine sending a quantum-encoded message from Earth to Mars. By entangling particles on both planets, we could manipulate one to imprint data onto its distant twin, effectively teleporting the information faster than light could carry it. China's Cheshire satellite has already demonstrated this, beaming entangled photons between ground stations over 700 miles apart. Future quantum networks could leverage this for unhackable communication, where any eavesdropping would instantly break the delicate entanglement, alerting both parties. But entanglement's implications stretch beyond technology. It hints at a universe where separation might be an illusion, where everything is subtly connected in ways we're only beginning to grasp. Some theories even suggest entanglement could explain spacetime itself, with every particle's quantum links weaving the fabric of reality. Whether it's two electrons or two galaxies, the cosmos might be far more intimate than we ever dreamed. So the next time you feel alone, remember, at some level, even the atoms in your hand might be whispering to particles on the other side of the universe, bound by a connection that laughs at the idea of distance. If entanglement made the universe feel strangely interconnected, the uncertainty principle pulls the rug out from under our attempts to understand it at all. Werner Heisenberg's groundbreaking idea reveals a cosmic joke. The more desperately we try to pin down a particle's location, the less we can know about its speed, and vice versa. It's not that our microscopes are too weak or our math too sloppy. This blurriness is woven into the fabric of reality itself. Imagine trying to photograph a hummingbird in mid-flight with a camera that, by design, either freezes its position perfectly but leaves its wings a blur, or captures the motion crisply while making the bird's location indistinct. That's the trade-off quantum mechanics forces upon us. This principle shatters the classical dream of a clockwork universe, where everything could, in theory, be predicted with absolute precision if we just had enough information. Newton's laws suggested that with perfect knowledge of an object's position and momentum, its future path could be calculated forever. But at the quantum scale, such certainty is impossible. The uncertainty principle doesn't just say we don't know both values. It says they literally don't exist simultaneously with exactness. A particle isn't hiding its speed from us while we measure its position. It genuinely lacks a well-defined momentum until we stop asking where it is. The implications ripple far beyond abstract physics. Consider the humble electron microscope. It works because we accept that we can't perfectly know an electron's momentum while pinpointing its position. By allowing some uncertainty in speed, we can use electrons like tiny flashlights, their wave-like properties illuminating details far smaller than visible light could reveal. Even your smartphone's GPS relies on this principle at the atomic level. The precision of its timing signals is ultimately limited by quantum uncertainty in the atoms of its onboard clocks. But the uncertainty principle isn't just about technical limitations. It forces a profound philosophical reckoning. Is the universe fundamentally fuzzy? Some interpretations suggest particles don't have definite properties until measured, while others propose that reality is a sea of probabilities, with exact values emerging only through interaction. This isn't just about small particles either. In theory, everything has quantum uncertainty. It's just that for large objects like baseballs or planets, the blurriness becomes so vanishingly small it's undetectable. But in the subatomic realm, this fuzziness dominates, making the quantum world a place of perpetual ambiguity. Perhaps the most startling consequence is how measurement itself changes what's being measured. Shine light on an electron to locate it, and the photons you use to see it will inevitably knock it off course, altering its momentum. It's like trying to measure the temperature of a snowflake with a flamethrower. The act of observation disrupts the very thing you're trying to study. This leads to mind-bending questions. If reality only sharpens into focus when observed, what does it look like when we're not looking? Does the moon exist in a definite state when no one's watching? Or is it too smeared across a range of possibilities until a conscious observer checks? The uncertainty principle doesn't just describe the universe, it redefines what it means to know something. In a realm where certainty is impossible, science becomes less about uncovering fixed truths and more about mapping probabilities. It's a humbling reminder that nature guards her deepest secrets fiercely, revealing just enough to keep us awestruck, but never enough to satisfy our hunger for absolute answers. And that might be the most quantum quirk of all. The universe isn't just stranger than we imagine. It's stranger than we can imagine. If quantum entanglement and uncertainty left you questioning reality, prepare for a quirk that defies one of our most basic assumptions: solid objects can't pass through each other. At our everyday scale, that's absolutely true. Try walking through a brick wall and you'll end up with nothing but a headache. But zoom into the quantum realm and the rules change entirely. Here, particles pull off the ultimate magic trick, quantum tunneling, where they vanish on one side of an impenetrable barrier and reappear on the other, as if the wall wasn't even there. This isn't theoretical speculation. Quantum tunneling is a well-documented phenomenon, and it's happening right now inside the Sun. The fusion reactions that power our star rely on protons overcoming their natural repulsion to collide and form helium. Classically, those protons don't have enough energy to smash through the electromagnetic barrier between them. But thanks to tunneling, there's always a tiny probability they'll cheat and slip through anyway. Without this quantum quirk, stars wouldn't shine, and life as we know it wouldn't exist. But tunneling isn't just a cosmic curiosity, it's the backbone of modern technology. Your computer's flash memory uses tunneling to store data. In NAND chips, electrons tunnel through an insulating layer to represent binary ones and zeros, allowing your phone to retain photos and files even when powered off. Even the humble touchscreen relies on quantum tunneling at the microscopic level, with electrons skipping across gaps in conductive materials to register your finger's touch. The secret behind this bizarre behavior lies in the wave-like nature of particles. Unlike a baseball thrown at a wall, which will always bounce back, a quantum wave doesn't stop abruptly at a barrier. Instead, it tapers off gradually, like a whisper fading into silence. And just as a whisper might still be faintly heard on the other side of a thin door, a particle's wave function can extend slightly beyond an obstacle. There's always a small chance the particle will materialize past the barrier, as if it phased through solid matter. The odds of tunneling depend on the barrier's width and height. Thinner barriers mean higher chances. That's why you don't see humans tunneling through walls. For an object as large and slow-moving as a person, the probability is so astronomically low it might as well be zero. But for tiny, fast-moving particles like electrons, tunneling happens constantly. In fact, it's the reason your enzymes work. The chemical reactions in your body rely on protons tunneling between molecules, speeding up processes that would otherwise take centuries. Some of the most cutting-edge technologies are pushing tunneling to its limits. Scanning tunneling microscopes can image individual atoms by precisely controlling electron tunneling between a sharp tip and a surface. Quantum tunneling composites are being developed for flexible electronics, where pressure changes the tunneling distance between particles, creating sensors that could one day give robots a human-like sense of touch. But perhaps the most mind-bending implication is that tunneling suggests reality is probabilistic at its core. A particle isn't squeezing through a barrier. It's appearing on the other side because its wave function never quite vanishes. This blurs the line between existence and probability, where a particle isn't strictly here or there, but exists as a spread-out cloud of potential until measured. It's yet another reminder that the quantum world operates on a logic entirely alien to our daily experiences. So the next time you charge your phone or bask in sunlight, remember, you're witnessing quantum tunneling in action. The universe doesn't just bend the rules, it rewrites them entirely, proving that even the most solid-seeming barriers are, at the subatomic level, more like fleeting suggestions than unbreakable laws. If quantum tunneling made barriers seem negotiable, vacuum fluctuations reveal an even deeper truth: nothingness is an illusion. What we call empty space is anything but empty. At the tiniest scales, the universe fizzes with activity as particles and their antimatter twins spontaneously burst into existence, only to annihilate each other moments later. This isn't poetic metaphor, it's measurable physics, proven by the Casimir effect. Place two uncharged metal plates incredibly close together in a vacuum, and they'll inexplicably pull toward each other. Why? Because the space outside the plates allows for more of these fleeting particle pairs than the narrow gap between them, creating a subtle pressure difference. The empty space between the plates is literally pushing them together. These vacuum fluctuations aren't random noise, they're the universe's quantum foam, a seething undercurrent of creation and destruction happening everywhere all the time. Imagine a calm ocean's surface hiding countless tiny bubbles constantly forming and popping beneath. Now scale that down to the Planck length, and you've got the fabric of spacetime itself, bubbling with ephemeral particles that borrow energy from the future to exist briefly before vanishing back into the void. Heisenberg's uncertainty principle makes this possible. There's always a tiny wiggle room in energy and time at quantum scales, allowing particles to momentarily cheat conservation laws. The implications are staggering. For one, this quantum foam might hold clues to dark energy, the mysterious force accelerating the universe's expansion. Some theories suggest vacuum fluctuations could be generating repulsive energy on cosmic scales, pushing galaxies apart. Others propose that if we could somehow harness or stabilize these fluctuations, we might unlock unfathomable energy sources, or even warp spacetime itself, bending the rules of relativity. But the weirdness doesn't stop there. Virtual particles from these fluctuations occasionally get a promotion to reality. Near black holes, intense gravity can rip apart particle-antiparticle pairs before they annihilate, with one falling in and the other escaping as radiation-hawking radiation, the slow leak that causes black holes to evaporate over eons. Even your own body emits photons thanks to these quantum whispers, a faint glow undetectable to the naked eye but real nonetheless. What's truly humbling is realizing how much of reality operates on credit. The universe is like a master accountant, balancing its books so precisely that these constant quantum loans never upset the cosmic ledger. Every cubic centimeter of space, even in the deepest void between galaxies, crackles with this hidden activity. So when you look up at the night sky, remember, you're not staring at emptiness. You're gazing at a vast, dynamic arena where existence itself flickers in and out like fireflies in the dark, proving once again that nothing in the quantum world is ever truly at rest. If superposition lets particles exist in multiple states at once, why don't we see cats, cars, or coffee cups in two places simultaneously? The answer lies in a phenomenon called quantum decoherence, the universe's way of hiding its strangeness from our everyday view. Imagine a drop of ink in a still pond. At first, it forms a clear, concentrated spot, but as water molecules jostle against it, the ink spreads, dissolving into the pond until it's indistinguishable from the surroundings. That's decoherence in action. Quantum systems start clean and isolated, their superpositions crisp and well-defined, but the moment they interact with their environment, whether it's air molecules, stray photons, or even cosmic rays, those delicate superpositions get scrambled, collapsing into the single, definite states we recognize in the classical world. This isn't just theoretical hand-waving. Lab experiments with tiny objects like buckeball soccer ball-shaped molecules made of 60 carbon atoms have shown quantum interference patterns, proving superposition at scales far larger than electrons. But as researchers push the boundaries, trying to observe quantum effects in even bigger systems, decoherence becomes the ultimate party crasher. Vibrations, temperature fluctuations, even the faintest electromagnetic fields act like noise drowning out a whisper, forcing quantum systems to pick a side. It's why Schrödinger's cat is either alive or dead in our macroscopic experience. Not both. The countless interactions inside the box destroy the superposition long before we lift the lid. But here's where it gets fascinating. Decoherence doesn't just erase quantum weirdness, it helps explain why the classical world feels so solid and predictable. The process is like a cosmic averaging effect, where trillions of quantum interactions per second smooth out the probabilities into what looks like certainty. Think of it like flipping a coin a million times. Individually, each flip is random, but the overall ratio will always trend toward 50-50. Decoherence does something similar, making quantum fuzziness statistically vanish at human scales. Yet the boundary between quantum and classical remains blurry. Scientists have observed quantum behavior in increasingly large objects, from viruses to tiny mechanical oscillators visible under microscopes. Some theories even suggest gravity might play a role in triggering decoherence, meaning the very fabric of space-time could be nudging quantum systems to make up their minds. Others propose that consciousness itself might influence the process, though that's a hotly debated idea. What's clear is that decoherence isn't a flaw in quantum mechanics. It's the mechanism that lets two seemingly contradictory worlds, the probabilistic quantum realm and the deterministic classical one, coexist. This has huge implications for quantum computing. Qubits rely on maintaining superposition long enough to perform calculations, but decoherence is their Achilles heel. That's why quantum computers operate at temperatures near absolute zero, shielded in vacuum chambers, to minimize environmental noise long enough to harness the quantum magic. In a way, building a quantum computer is like trying to keep that ink drop perfectly contained in the pond, resisting nature's urge to spread it thin. So while we might never see a tennis ball in two places at once, decoherence isn't just a limitation, it's the reason reality feels stable enough for life to exist. It's the universe's delicate balancing act, allowing quantum rules to govern the microscopic while presenting a familiar, predictable world to creatures like us. And that's the real quirk. The weirdness never truly goes away. It's just hiding in plain sight beneath every seemingly ordinary moment. The observer effect takes the quantum world's strangeness and cranks it up to 11. Imagine setting up a camera to record a shy performer only to realize the moment you hit record, their entire act changes. That's essentially what happens at the subatomic level. Particles don't just passively exist, waiting to be measured. The act of observation actively reshapes their behavior. This isn't a limitation of our tools, it's a fundamental feature of reality. The classic double-slit experiment lays it bare. When electrons aren't observed, they behave like waves, creating interference patterns. But the instant you try to catch which slit they pass through, they snap into particle-like behavior, as if embarrassed by the attention. This raises a dizzying question. Does reality require an observer to crystallize? Some interpretations of quantum mechanics suggest that without measurement, particles remain in a haze of probabilities, a notion that edges uncomfortably close to philosophy. The Copenhagen interpretation, championed by Niels Bohr, argues that quantum systems only choose definite states upon interaction with a measuring device or conscious observer. It's as if the universe hesitates until someone or something looks like a tree falling in a forest with no ears to hear. But here's where things get thorny. What counts as an observer, a photon hitting a detector, a human eye registering the result? The debate splits physicists into camps, with some arguing consciousness plays a unique role, while others insist any interaction with the environment suffices to collapse the wave function. Practical implications abound. Quantum cryptography leverages the observer effect to create unhackable communication. Any eavesdropper's attempt to measure the system would alter it, leaving a glaring footprint. Even your digital camera's sensor relies on this principle. Every pixel click is a tiny observation, collapsing photons into measurable signals. But the weirdest applications lie in delayed choice experiments, where decisions made after a particle's journey seem to retroactively determine its behavior. It's like discovering that flipping a coin today could change how it landed yesterday, a notion that makes even seasoned physicists pause. The observer effect blurs the line between science and metaphysics. If reality remains indefinite until measured, does that mean the moon isn't there when we're not looking? Or is measurement simply any interaction that leaves a mark, from a photon bouncing off an atom to a cat pawing at a Geiger counter? The answers might redefine not just physics but our place in the cosmos. One thing's certain, in the quantum realm, watching isn't passive, it's participatory. And that might be the most humbling quirk of all. Quantum immortality sounds like the plot of a sci-fi thriller, but it emerges straight from the cold, hard math of quantum mechanics, specifically the many worlds interpretation. Picture this: every time a quantum system faces a choice, like a radioactive atom decaying or not, the universe doesn't pick one outcome. Instead, it splits, spawning parallel realities where every possible result plays out. Now apply that logic to life and death. If every quantum event branches reality, then there's always a version of you where the statistically unlikely keeps happening, where the bullet misses, the parachute opens, the heartbeat continues. In some corner of the multiverse, you'd never experience death, only an unbroken chain of survival against all odds. This isn't just philosophical musing. The thought experiment gained traction when physicists like Max Tegmark explored its implications. Imagine playing Russian roulette with a quantum trigger, a device that fires or doesn't based on a random atomic decay. In most branches, the gun fires, and that version of you ceases to experience anything. But in the rare branch where it doesn't, you'd keep playing again and again, each survival spawning new realities where you inexplicably cheat death. To an outside observer, your luck would seem impossible, but from your perspective, you'd only ever witness the universes where you're alive. It's like flipping a coin 1,000,000 times and always seeing heads, not because the coin is rigged, but because every tail's outcome erases your ability to observe it. Critics dismiss quantum immortality as a misinterpretation of probability, arguing that consciousness can't skip unfavorable outcomes. Yet the idea forces us to grapple with profound questions. If the multiverse is real, does subjective experience latch onto the most favorable branches? And what does immortality even mean in a cosmos where infinite versions of you die constantly, while one thread continues indefinitely? The thought experiment blurs the line between physics and metaphysics, challenging our understanding of identity, continuity, and the nature of existence itself. Beyond existential dread, this quirk has practical implications. It tests the limits of the many worlds interpretation, pushing physicists to refine their models. Some propose that quantum immortality, if taken seriously, would require consciousness to play an active role in reality, a controversial idea that edges into the territory of quantum mind theories. Others argue it's a reductio ad absurdum, highlighting flaws in how we interpret probability across parallel worlds. Either way, it's a reminder that the universe's quirks aren't just abstract equations. They force us to confront what it means to be alive, to observe, and to persist in a reality far stranger than we ever imagined. So the next time you narrowly avoid a collision or wake from a high fever, consider this. In some branching timeline, maybe you didn't. Quantum immortality isn't about cheating death. It's about realizing how deeply interconnected all possible outcomes might be, and how little we truly understand about the fabric of existence. And that's the real mind bender. The multiverse doesn't just contain alternate histories. It might contain alternate versions of you living every possible life and death imaginable. Just when you thought quantum mechanics couldn't get any stranger, along comes the quantum Zeno effect, a phenomenon so counterintuitive it feels like hacking the universe's code. Imagine if you could freeze a pot of water mid-boil simply by staring at it. That's essentially what happens in the quantum realm when you observe a system obsessively. Named after the ancient Greek philosopher Zeno, who famously argued that motion is an illusion, this effect reveals how measurement itself can trap particles in a single state, suspending time at the subatomic level. Here's how it works. Unstable quantum systems, like radioactive atoms, decay randomly over time. But if you bombard them with rapid-fire observations, say, checking their state 1 trillion times a second, their wave functions never get the chance to evolve. It's like trying to flip a light switch while someone keeps slapping your hand away. The system gets stuck, not because of any physical barrier, but because constant measurement resets its quantum clock. Labs have demonstrated this with beryllium ions suspended in magnetic fields. When left alone, these ions quickly flip their spin states, but under relentless laser monitoring, they freeze like deer in headlights, defying their natural instability. The implications are staggering for quantum computing. Qubits are notoriously fragile, their superpositions collapsing at the slightest disturbance, a problem called decoherence. But by strategically applying the Zeno effect, scientists can artificially extend qubit lifetimes, effectively locking them into useful states long enough to perform calculations. Think of it as hitting pause on a quantum stopwatch, giving engineers precious extra milliseconds to manipulate information. Some prototypes already use this trick, pulsing microwave or laser measurements to shield qubits from environmental noise. It's like teaching a gymnast to balance indefinitely by constantly whispering corrections before they start to wobble. But the Zeno effect isn't just a laboratory curiosity. It might operate in nature too. Certain photosynthetic bacteria appear to exploit a similar principle, using molecular vibrations to measure energy pathways repeatedly, preventing wasteful dissipation and maximizing efficiency. This could explain why quantum coherence persists in warm, messy biological systems, defying expectations that such delicate states require frigid isolation. Nature, it seems, has been using quantum observation as a tool long before we understood it. Of course, there's a flip side, the anti-Zeno effect. If observations are poorly timed, too frequent or too sparse, they can actually accelerate decay, like overcooking a dish by constantly opening the oven. This delicate balance between observation and interference underscores how deeply measurement shapes quantum reality. It's not just about what we know, it's about how often we ask. Philosophically, the Zeno effect blurs the line between observer and participant even further. If watching a system can alter its behavior so drastically, does that mean reality is, in some sense, a dialogue between the universe and those probing it? Or is it simply a quirk of statistics where probability waves collapse under relentless scrutiny? Whatever the answer, one thing's clear. In the quantum world, paying attention isn't passive, it's transformative. And that might be the most powerful quirk of all. After diving into the mind-bending effects of observation and measurement, we arrive at a quirk that might explain why we all agree on what's real, even when the quantum world seems anything but. Quantum Darwinism is the idea that reality as we experience it isn't just random, it's the result of a subtle, invisible selection process. Think of it like evolution, but instead of organisms competing for survival, quantum states compete for permanence. The ones that withstand constant interactions with their environment, the ones that get copied over and over, are the ones we end up perceiving as concrete. Take the chair you're sitting on. At the quantum level, its atoms exist in a haze of probabilities, with electrons buzzing around in fuzzy clouds of possibility. But somehow, trillions of these uncertain particles come together to create an object that feels solid, stable, and unmistakably real to everyone who touches it. Quantum Darwinism suggests this isn't an accident. The chair's specific arrangement of atoms persists because it's constantly interacting with air molecules, light, and even your own body, each interaction reinforcing its state while less stable configurations fade away. It's as if reality itself is crowdsourced, with the most resilient quantum states winning by being repeatedly observed and replicated by the environment. This idea helps solve one of quantum mechanics' biggest puzzles, the measurement problem. Why do quantum superpositions collapse into definite states when measured? Why don't we see macroscopic objects in two places at once? Quantum Darwinism proposes that the environment acts as a relentless observer, continuously measuring systems in a way that filters out fragile superpositions. Only the most robust states, those that can withstand this constant scrutiny, survive long enough to shape our shared experience. Imagine 1,000 photographers snapping pictures of a sculpture from every angle. The images that match, the ones where the sculpture looks the same, are the ones we collectively accept as true, while the outliers get discarded. The implications stretch far beyond philosophy. Quantum Darwinism could explain why certain molecular structures are more common in nature, or why biological systems seem to exploit quantum effects with such precision. If a quantum state helps a protein fold more efficiently or a plant absorb sunlight more effectively, that state gets selected by its environment, propagating through countless interactions. Even the arrow of time, the fact that we remember the past but not the future, might emerge from this process, with the most stable states leaving lasting imprints on the world around them. Critics argue that quantum Darwinism doesn't fully explain how certain states become privileged, or why our perceptions align so perfectly, but it's a compelling framework, blending quantum theory with Darwinian thinking to bridge the gap between the probabilistic subatomic realm and the seemingly solid world we navigate daily. So the next time you reach for a doorknob or watch a sunset, remember, you're not just observing reality. You're participating in a grand, invisible competition where only the most persistent quantum states get to shape what we call real. And that consensus isn't magic. It's the universe's way of filtering chaos into coherence, one interaction at a time. Einstein never liked the idea of spooky action at a distance, and the EPR paradox was his way of calling quantum mechanics incomplete. Picture this: you and a friend each take one glove from a pair, one left, one right, without looking, then travel to opposite ends of the galaxy. The moment you check your glove and see it's left-handed, you instantly know your friend's is right-handed, no signal needed. Classical physics says this makes sense because the glove's handedness was predetermined, but quantum mechanics says something far stranger. Entangled particles don't have predetermined states at all. They exist in superposition until measured, and somehow the act of measuring one here instantly sets the state of its partner there, no matter how far apart they are. To Einstein, this implied either faster-than-light communication, which relativity forbids, or a glaring hole in quantum theory. The crux of the paradox lies in locality. The principle that objects can't influence each other faster than light can travel between them. Einstein argued that if quantum mechanics allowed entangled particles to coordinate instantly across vast distances, the theory must be missing hidden variables, unknown properties that predetermine particle states, making the universe local and deterministic after all. For decades, this seemed like a philosophical debate. Then came physicist John Bell, who devised a way to test it. Bell's theorem showed that if hidden variables existed, entangled particles would correlate in a certain statistical way. But experiment after experiment, including groundbreaking work by Elaine Aspect in the 1980s, revealed correlations too strong for any local hidden variable theory to explain. The universe, it seemed, was genuinely non-local. This doesn't just challenge relativity, it redefines what we mean by separate. Entangled particles behave as if they're part of a single system, their properties intertwined regardless of distance. It's not that information travels faster than light, it's that the particles were never truly independent to begin with. Think of it like two sides of a coin. Flipping one doesn't send a signal to the other. The outcome was always linked by the coin's structure. Quantum entanglement suggests the universe might operate similarly, with particles sharing a deeper connection that transcends space and time. Practical applications are already emerging. Quantum networks use entanglement to create unhackable encryption, where any eavesdropper's attempt to intercept particles would break their delicate linkage, alerting both sender and receiver. Future quantum internet protocols could rely on this very spookiness to transmit data securely across the globe, but the implications stretch far beyond technology. If particles can coordinate instantaneously across cosmic distances, does that mean the universe is fundamentally interconnected in ways we're only beginning to grasp? Some theories even propose that spacetime itself emerges from a vast web of quantum entanglements, a notion that could reshape our understanding of gravity, black holes, and the fabric of reality. Einstein may have been wrong about quantum mechanics being incomplete, but his skepticism forced physicists to confront the paradox head-on. The EPR paradox isn't just a historical footnote, it's a living challenge, pushing us to reconcile quantum weirdness with the rest of physics. And that tension between the world we see and the rules beneath it might be exactly what leads us to the next great breakthrough. After all, the universe doesn't owe us intuitive explanations, it's our job to catch up. If entangled particles seem like magic, quantum teleportation takes the trick to the next level. No wands required. Forget Star Trek's glittering transporter beams. This isn't about moving matter through space. Instead, it's about transferring the exact quantum state of a particle, its unique identity, so to speak, across any distance instantly without the particle itself ever making the journey. Imagine mailing a snowflake's intricate pattern by destroying the original and perfectly reconstructing it elsewhere, down to the last microscopic detail. That's the essence of quantum teleportation, and it's not science fiction. It's been achieved in labs worldwide, even across continents. Here's how it works. Start with a pair of entangled particles, like two photons linked in perfect sync. Keep one, let's call it photon A, at your lab, and send its entangled partner, photon B, to a distant location, say, a satellite orbiting Earth. Now, introduce a third photon, photon C, the one whose quantum state you want to teleport. By performing a special measurement on photon A and photon C together, you create a sort of quantum handshake. This measurement entangles them, but it also disrupts their states, a necessary sacrifice. The magic happens when you send the results of that measurement to the holder of photon B via classical communication, like a radio signal. Using that information, they can perform precise adjustments on photon B, transforming it into an exact replica of photon C's original state. The original photon C is gone, its information obliterated by the measurement, but its quantum essence now lives on in photon B, light years away. What makes this mind-bending isn't just the distance, it's the fact that no physical particle traveled the gap. The information about photon C's state wasn't carried by photon B. It was recreated using the spooky link of entanglement and a bit of classical data. This avoids relativity's speed limit because the actual transmission happens at light speed via the radio signal, while the quantum correlation is instantaneous. It's like whispering a secret to a friend on the other side of the world by first sharing a pair of synchronized codebooks. The whisper itself is slow, but the meaning leaps across instantly. The applications are staggering. Quantum teleportation could form the backbone of a future quantum internet, where data is transmitted with unhackable security. Since any eavesdropper would disrupt the entanglement, interception is impossible without leaving a trace. China's Misha satellite has already demonstrated this, teleporting quantum states between ground stations over 700 miles apart. But the implications go beyond tech. This process challenges our deepest notions about information and reality. If a particle state can exist in one place, vanish, and reappear elsewhere without traversing the space in between, does location even mean the same thing at quantum scales? Of course, there are limits. Quantum teleportation can't clone states. The original is always destroyed, obeying the no-cloning theorem. And while it's instantaneous in one sense, the need for classical communication means it's not faster than light in practice. But as we refine the technology, we're inching toward a world where quantum networks could link cities, nations, even planets, with a level of security and precision classical physics could never match. So while you won't be teleporting to Mars for lunch anytime soon, the universe's quirks are handing us something just as revolutionary: the ability to move information itself in ways that defy every intuitive rule of the game. Just when you thought quantum mechanics couldn't get any weirder, meet the quantum Cheshire Cat, an effect so strange it makes Lewis Carroll's grinning feline look downright ordinary. In the subatomic world, particles can pull off a trick even the Mad Hatter couldn't explain. Their properties, like spin or polarization, can detach from the particles themselves, lingering like a ghostly afterimage long after the original has moved on. Imagine stroking a cat and feeling its purr vibrate in your hands, only to turn around and realize the cat left the room minutes ago, its purr somehow lingering behind. That's the essence of this quantum quirk, where the universe seems to tease us by separating the map from the territory. The first experimental proof came in 2014, when researchers used neutron beams and cleverly placed filters to catch a neutron spin property existing in a different location than the neutron itself. Here's how it works. Neutrons, like all quantum objects, behave as both particles and waves. By setting up an interferometer, a device that splits and recombines particle waves, scientists could guide neutrons along two paths simultaneously, thanks to superposition. But here's the twist: they inserted filters along one path that interacted only with the neutron's spin, not its physical position. When the neutron waves recombined, measurements showed the particle had traveled one path while its spin had taken the other, like a hiker leaving their shadow behind on a parallel trail. This isn't just a parlor trick. The quantum Cheshire Cat effect forces us to rethink what we mean by an object. In everyday life, we assume a thing's properties are inseparable from the thing itself. A red apple can't be red if the apple isn't there. But quantum mechanics laughs at this assumption. Properties like spin or charge aren't just stickers slapped onto particles. They're dynamic, detachable aspects of a deeper, more fluid reality. It's as if the universe keeps its ingredients list separate from the dish, allowing flavors to linger even when the meal is gone. Practical implications are already emerging. Quantum metrology, the science of ultra-precise measurement, could leverage this effect to probe materials without disturbing them. Imagine studying a fragile biological sample by detecting its magnetic properties without bombarding it with particles that might cause damage. Or consider quantum computing, where information could be encoded in disembodied spins, potentially reducing interference between qubits. Even cryptography might benefit, with property-only signals offering new ways to transmit data undetected. But the real magic lies in the philosophical shake-up. If a particle's identity isn't tied to its properties, what does define it? Is an electron still an electron if its spin is elsewhere? The Cheshire Cat effect suggests that at the quantum level, objects might be more like abstract relationships than standalone entities, a network of shifting attributes rather than solid things. This echoes ancient philosophical debates about whether a ship remains the same ship if all its planks are replaced, but with a quantum twist. Now the planks don't even need to be attached to the ship at all. Critics argue this effect is more about clever measurement than true physical separation, but even they admit it reveals how deeply our classical intuitions fail in the quantum realm. After all, if a grin can exist without a cat, what else might be possible? The answer, it seems, is limited only by how boldly we're willing to question the nature of reality itself. And that's the true lesson of the quantum Cheshire Cat. Sometimes the most profound discoveries begin by chasing a smile that forgot to stick around. If the quantum Cheshire Cat left you questioning where a particle's properties truly reside, time crystals will make you wonder when, or even if they ever stay still. Imagine a snowflake that doesn't just repeat its pattern in space but in time, cycling through the same motions over and over without ever melting or needing a push. That's the essence of a time crystal, a bizarre phase of matter that defies one of physics' most sacred principles, the idea that perpetual motion is impossible. Unlike a pendulum that eventually stops without energy, time crystals oscillate indefinitely in their lowest energy state, like a cosmic clock that winds itself. The concept was first proposed by Nobel laureate Frank Wilczek in 2012, initially met with skepticism. Critics argued it violated thermodynamics. How could something change endlessly without energy input? But by 2017, labs had created time crystals using chains of ytterbium atoms or nitrogen vacancies in diamonds. The key lies in discrete time symmetry breaking. Normally, if you poke a system periodically, say, flipping a light switch every second, its response will sync with your pokes. Time crystals break this symmetry. They respond at a different rhythm, like a drumbeat that echoes at half the speed of the drummer's sticks, locked into their own stubborn tempo. What makes them truly revolutionary isn't just their defiance of equilibrium. Time crystals exist in a state of non-ergodicity, meaning they never settle into thermal equilibrium like everything else in the universe. A cup of coffee left alone cools to room temperature. Stars exhaust their fuel and fade. But time crystals, they're the universe's first known structures that resist this cosmic leveling, dancing forever in their own private rhythm. Think of them as the subatomic equivalent of a music box that never winds down, its melody looping eternally, not because it's immune to friction, but because friction somehow fuels its motion. Practical applications are already shimmering on the horizon. Quantum computers plagued by decoherence could use time crystals as stable memory units, their unshakable rhythms preserving information longer than fragile qubits. Precision sensors might leverage their perfect periodicity to measure time or magnetic fields with unprecedented accuracy. Some theorists even speculate that time crystals could model exotic physics like black hole dynamics or early universe conditions, acting as miniature cosmic simulators in the lab. But the deepest implications are philosophical. Time crystals force us to redefine what stable even means. If matter can oscillate endlessly without energy, does that mean perpetual motion isn't forbidden, just relegated to the quantum realm? Could the universe itself harbor hidden time crystalline structures, ticking silently beneath the fabric of space-time? One thing's certain, in a cosmos where matter can move without moving forward, time itself might not flow the way we think, and that's a quirk that doesn't just bend the rules, it rewrites them entirely. Quantum annealing sounds like something straight out of a sci-fi novel, but it's one of nature's most elegant problem-solving tricks. Picture standing in a mountain range at night, blindfolded with one goal: find the lowest valley. In the dark, you'd have to feel your way down, step by step, risking getting stuck in a small dip without realizing a deeper valley lies just beyond the next ridge. That's how classical computers tackle optimization problems, calculating every possible route, one at a time, often hitting dead ends or local minima. But quantum annealing, It's like removing the blindfold and gaining the ability to tunnel through mountains, exploring the entire landscape at once to pinpoint the absolute lowest point. The secret lies in quantum fluctuations, those tiny, random jumps particles make even at frigid temperatures near absolute zero. In a quantum annealer, these fluctuations act like a built-in GPS, letting the system explore countless solutions simultaneously without getting trapped in suboptimal valleys. Here's how it works. Start with a problem encoded into a web of quantum bits, or qubits, where each possible solution is represented by a different energy landscape. Initially, the system is hot with quantum noise, allowing qubits to explore freely. Then, slowly cool the system while tuning the fluctuations. Like water finding its level, the qubits settle into the lowest energy configuration, the optimal solution guided by the natural tendencies of quantum mechanics. D-Wave, the pioneer in commercial quantum annealing, has already demonstrated this power in real-world scenarios. Take airline scheduling, where minimizing fuel costs while maximizing passenger connections is a nightmare of variables. Classical supercomputers might take weeks to crunch the numbers, but a quantum annealer can evaluate all possible routes at once, factoring in weather, crew shifts, and maintenance in a fraction of the time. Or consider drug discovery, where molecules must fold into precise shapes to bind with targets. Quantum annealing explores every possible folding pathway simultaneously, accelerating the search for life-saving medications. Even artificial intelligence benefits, with machine learning models training faster by sidestepping the computational quirks, and that bogs down classical algorithms. But here's the catch: quantum annealing isn't a magic bullet. It excels at specific problems, combinatorial optimizations, where you're sifting through a dizzying number of possibilities to find the best arrangement. Think traffic flow optimization, stock portfolio balancing, or even cracking cryptographic puzzles. For other tasks, like simulating quantum chemistry or running Shor's algorithm, gate model quantum computers still reign supreme. Yet the beauty of annealing lies in its simplicity. Unlike error-prone universal quantum computers, annealers don't need perfect qubits or complex error correction. They embrace the noise, using it as a tool rather than fighting it. Philosophically, quantum annealing feels like tapping into the universe's own problem-solving playbook. After all, nature doesn't brute force its way to efficiency. It lets probabilities and energy landscapes guide the way. From protein folding to the formation of galaxies, optimization is woven into the fabric of reality. By harnessing these principles, we're not just building better computers, we're learning to think like the cosmos itself. And that might be the ultimate hack, solving humanity's toughest puzzles by letting quantum physics do what it does best: explore, adapt, and find the path of least resistance. What if the universe around us, the stars, the planets, even your own hands, is nothing more than an incredibly convincing illusion? The holographic principle dares to suggest exactly that, proposing that our three-dimensional reality might be a projection of information encoded on a distant two-dimensional surface. Think of it like a movie screen. The images appear deep and lifelike, but peel back the illusion, and you'll find everything traced back to flat, flickering pixels. If this sounds like science fiction, consider that some of the brightest minds in physics take it seriously, not as metaphor, but as a possible blueprint for how space-time itself operates. The idea first gained traction in the 1990s when physicists studying black holes stumbled onto a paradox. They realized the information describing everything swallowed by a black hole couldn't just vanish, it had to be preserved somehow, in line with quantum mechanics. But where the answer shocked them, the information might be smeared across the black hole's event horizon. the point of no return, like a cosmic fingerprint pressed into its two-dimensional surface. From there, the leap wasn't so far to imagine that all reality might work this way, that the universe's entire contents could be written on some vast, unseen boundary, with our 3D experience just a high-resolution playback. Experiments are already probing this radical notion. Fermilab's holometer, for instance, searches for telltale quantum fuzz in space-time tiny fluctuations that might betray its pixelated, holographic nature. So far, no smoking gun, but the search continues. Meanwhile, string theorists have found mathematical hints that the holographic principle could unify gravity and quantum mechanics, two forces that stubbornly resist playing nice in conventional models. It's as if the universe handed us a jigsaw puzzle where the pieces only fit when you flatten the box. The implications are staggering. If the holographic principle holds, it means the cosmos operates like a colossal quantum computer, with every event, from a supernova's explosion to your morning coffee cooling, rendered in real time by underlying code we can't yet read. It would redefine what real even means. After all, in a video game, the world feels solid until you glitch through a wall and see the scaffolding beneath. Could our universe have similar seams? Some interpretations even suggest that time and space might emerge from something more fundamental, a vast network of quantum entanglements, like threads weaving a tapestry of perception. Skeptics argue that without direct evidence, the holographic principle remains speculative, but its allure lies in its audacity. It doesn't just tweak our understanding of reality, it upends it entirely, suggesting that the richness of our 3D world, the textures, the depths, the distances might be a shadow play cast by something infinitely stranger. So the next time you reach out to touch something solid, ask yourself, are you feeling an object or just the universe's most convincing mirage? For all the mind-bending quirks we've explored so far, one glaring gap remains in our understanding of the cosmos: the complete absence of a theory that unites quantum mechanics with gravity. Picture this: quantum physics governs the tiny world of particles with astonishing precision, while Einstein's general relativity flawlessly describes the dance of planets and black holes. Yet when we try to mash these two rulebooks together, the universe hands us a blank page. This isn't just an academic puzzle. It's a cosmic-sized contradiction that could hold the key to everything from the birth of the universe to the fabric of space-time itself. Enter loop quantum gravity, one of the boldest attempts to solve this riddle. Instead of imagining space as a smooth, continuous sheet the way relativity does, this theory proposes space-time is woven from tiny, indivisible loops, like a cosmic tapestry knit from threads a billion trillion times smaller than an atom. These loops form a network where quantized areas and volumes replace the infinite smoothness of classical physics. The result, a universe where not just matter, but space and time themselves are pixelated. Black holes under this model might not have singularities at their cores, but instead hit a density limit where space can't be crushed any further, like a compressed spring that simply won't budge. Then there's string theory, the flashier contender in this unification race. It swaps point-like particles for vibrating strings so small that if you scaled one up to the size of a tree, an atom would dwarf the Milky Way. These strings hum at different frequencies, producing every particle and force in nature like notes on a cosmic violin. But here's the catch: string theory demands extra dimensions, 6 or 7 more than we experience, curled up so tightly we'd never notice them. Think of a garden hose. From afar, it looks one-dimensional, but up close, it's a cylinder with a hidden circular dimension. String theory suggests our universe might be similarly wrapped in unseen geometries, with gravity perhaps leaking into other dimensions, explaining why it feels so weak compared to other forces. The stakes couldn't be higher. A working theory of quantum gravity wouldn't just tidy up physics, it would rewrite our origin story. The Big Bang, under current models, is a mathematical singularity where equations break down. But with quantum gravity, we might peer beyond that veil, understanding what, if anything, came before. It could reveal whether time is fundamental or emergent, whether space is relational or absolute, and whether black holes preserve information or erase it forever. Some theories even suggest space-time itself might be an illusion, emerging from deeper quantum connections like a 3D hologram projected from a 2D surface. Yet for all their brilliance, these theories face brutal challenges. Loop quantum gravity struggles to reproduce general relativity's successes on cosmic scales, while string theory's extra dimensions remain frustratingly untestable with current technology. Some physicists joke that string theory is a part of 21st century physics that fell into the 20th century by mistake, elegant math in search of experimental proof. Others argue we're missing a radical third path, something as shocking as relativity was to Newtonian physics. What's undeniable is this: the first person to crack quantum gravity won't just win a Nobel Prize, they'll unveil a new layer of reality, one that might make today's quantum quirks look like child's play. Until then, we're left with a universe that whispers its secrets in two different languages, daring us to become fluent in both. And that's the real quirk, not just that gravity resists quantization, but that its stubborn silence might be the universe's way of hinting at truths far stranger than we've yet imagined. The measurement problem is quantum mechanics' deepest philosophical wound, a puzzle so profound that even after a century, physicists still can't agree on what actually happens when we observe a quantum system. Take Schrödinger's infamous cat, suspended in that eerie blend of life and death. The math says it's in superposition until someone opens the box. But what exactly flips the switch from both to one? What collapses the wave function from a spread-out cloud of possibilities into a single, concrete reality? The answers range from the poetic to the downright surreal, and none of them come with a guarantee. First, there's the Copenhagen interpretation, the old god of quantum theory. Pioneered by Niels Bohr and Werner Heisenberg, it treats the wave function as a mathematical tool, a way to calculate probabilities, not a literal description of reality. In this view, measurement isn't passive, it's an interaction that forces the system to pick a state. But here's the rub: Copenhagen doesn't define what counts as a measurement. Is it a photon hitting a detector, a human squinting at a screen? The ambiguity leaves room for wild speculation, like Eugene Wigner's twist, that consciousness itself might be the trigger. His thought experiment imagined a friend sealed in a lab, observing the cat while Wigner stood outside. If the friend's observation collapsed the wave function, did Wigner's own consciousness later collapse the friend's superposition? It's a hall of mirrors where the observer becomes the observed, and reality hinges on who's paying attention. Then there's the many worlds interpretation, which sidesteps collapse entirely. Proposed by Hugh Everett in the 1950s, it suggests the wave function never actually collapses. Instead, every possible outcome branches off into its own parallel universe. In this multiverse, the cat isn't dead or alive. There's one world where it purrs and another where it doesn't, and both are equally real. No mysterious observer effect, no privileged role for consciousness, just an ever-expanding tree of alternate realities. Critics call it extravagant, but fans argue it's the cleanest math in town, preserving the Schrödinger equation without tacking on extra rules. But wait, what if the problem isn't with the wave function at all? Objective collapse theories like Gerardi-Rimini-Weber propose that superpositions decay spontaneously over time, with no observer needed. Tiny, random fluctuations nudge particles into definite states, ensuring the quantum weirdness stays mostly microscopic. It's like a cosmic failsafe, preventing cats or people from blurring into superpositions. Experiments hunting for these spontaneous collapses are underway, but so far, nature's keeping its secrets. Meanwhile, quantum decoherence offers a subtler take. Wave functions don't collapse so much as get lost in the noise. When a quantum system interacts with its environment, air molecules, stray photons, even distant stars, its delicate superpositions leak into the surroundings, becoming irretrievably scrambled. From our perspective, the system appears to snap into one state, but really, it's just entangled with the universe's vast, messy ledger. This view bridges quantum and classical realms without invoking consciousness or parallel worlds, but it still leaves a nagging question. Why do we only perceive one outcome? The measurement problem isn't just academic quibbling. Crack it, and we might finally understand why the quantum realm feels so alien compared to our everyday experience. It could redefine what we mean by reality, observation, even time. Until then, every interpretation is a flashlight in the dark, illuminating one corner of the mystery while leaving the rest in shadow. So the next time you check your phone or glance at the stars, remember, the act of looking might be doing far more than you think. We've seen quantum mechanics rewrite the rules for particles in labs and black holes in deep space. But what if life itself has been tapping into these quirks all along? Quantum biology is the startling idea that nature, over billions of years of trial and error, may have evolved ways to harness quantum weirdness for survival. Take photosynthesis, the process plants use to turn sunlight into energy. At its core lies a phenomenon called quantum coherence, where photons of light are absorbed by chlorophyll molecules, and their energy gets shuttled through a network of proteins with near-perfect efficiency. Classical physics would expect this energy to bounce around randomly, losing precious bits as heat. But experiments reveal something extraordinary. The energy explores all possible paths simultaneously, like a traveler testing every route in a maze at once before choosing the most efficient one. It's as if plants perform quantum computations without thinking, leveraging superposition to outsmart classical inefficiencies. Then there's the mystery of bird migration. Every year, European robins navigate thousands of miles using Earth's faint magnetic field, a feat that baffled scientists until quantum entanglement entered the conversation. Researchers now believe a protein in the bird's eyes, cryptochrome, may host entangled electron pairs. When light hits these molecules, the electron spins react to magnetic fields, creating a chemical signal the bird can interpret as a compass. What's wild is that this quantum effect persists in warm, wet, messy biological environments, conditions where lab-based quantum systems usually crumble in milliseconds. Nature, it seems, found a way to protect quantum coherence at room temperature, something our best engineers still struggle to replicate. Even your nose might be a quantum detector. The prevailing theory of smell-suggested molecules fit into receptors like keys in locks, but some scans defy this, like sulfur and boron compounds that smell identical despite wildly different shapes. Quantum tunneling could explain it. As odor molecules vibrate, electrons tunnel across receptors, creating a signature pattern your brain reads as rotten eggs or mint. It's a controversial idea, but if true, every time you sniff coffee or fresh-cut grass, you're experiencing quantum mechanics firsthand. The implications are staggering. If life exploits quantum effects, we might borrow nature's playbook to design ultra-efficient solar cells, bio-inspired quantum sensors, or even medicines tailored using quantum biology principles. Imagine cancer drugs that target tumors with pinpoint accuracy by hijacking quantum tunneling pathways, or artificial photosynthesis systems that solve our energy crises by mimicking plants' quantum tricks. Some scientists speculate that quantum biology could be the missing link between quantum physics and consciousness, though that's a leap even for the boldest theorists. Skeptics argue these phenomena could still have classical explanations, and they're right to demand rigor, but the evidence is mounting that evolution, faced with survival's harsh math, stumbled upon quantum solutions we're only now beginning to understand. It's a humbling thought. The same rules that govern entangled particles in lab vacuums might also pulse through the veins of a migrating robin or the leaves of an oak tree. And if nature cracked the quantum code billions of years ago, what other secrets might life be hiding in plain sight? The answers could rewrite not just biology, but our place in a universe where the line between the living and the quantum is far thinner than we ever dared imagine. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or at least that's what Stephen Hawking's calculations once suggested. Imagine tossing a book into a fire. The pages burn, but the smoke and ash still carry traces of the ink, the binding, the words. In theory, you could reconstruct the book from its remains. But Hawking radiation, the faint glow black holes emit as they slowly evaporate, seem to offer no such clues. According to his early work, the radiation was purely thermal, random noise with no connection to the stars, planets, or atoms the black hole had devoured. If true, the information describing those objects would be erased from the universe forever, violating a sacred principle of quantum mechanics. Information must never be destroyed. This clash between quantum theory and gravity became known as the black hole information paradox, and it sparked a decades-long battle among physicists. On one side, Hawking and others argued that black holes truly were the universe's ultimate erasers, their event horizons acting like one-way firewalls that scrambled information beyond recovery. This idea horrified quantum purists who saw it as a fatal flaw in our understanding of reality. If information could vanish, the entire framework of cause and effect, the idea that the past shapes the future in a predictable way, would crumble. It would mean the universe has a built-in delete button, and we're all just temporary files waiting to be wiped. Then came the counter-arguments. Leonard Susskind and Gerard T. Hooft proposed a radical alternative. Information isn't lost, it's encoded on the black hole's event horizon like a hologram, then slowly leaked back into the universe via Hawking radiation. Think of it like boiling a pot of alphabet soup. The letters seem to disappear as the broth evaporates, but if you could capture every steam molecule, you'd find the letters hidden in the vapor. This holographic principle suggests black holes don't destroy information, they just translate it into a language we're only beginning to decipher. Recent breakthroughs have tilted the scales toward Susskind's camp. In 2016, Hawking himself revised his stance, conceding that information might escape after all, not through the radiation itself, but via subtle quantum correlations at the event horizon. Even more tantalizing, simulations of holographic black holes using quantum computers have shown information can indeed survive evaporation, scrambled but not erased. The key might lie in wormholes, or rather, their quantum doppelgangers. Einstein-Rosen bridges, long dismissed as mathematical quirks, now appear to play a role as quantum tunnels preserving entangled information between the black hole's interior and the outgoing radiation. But the paradox isn't fully resolved. If information escapes, where does it go? Is it smeared across the cosmos or trapped in microscopic remnants? Some theories suggest black holes might leave behind Planck stars or fuzzballs, exotic remnants encoding their swallowed histories. Others propose that spacetime itself is built from quantum entanglement, meaning black holes don't hold information at all. They're just knots in the universe's quantum network, waiting to be untangled. The stakes are cosmic. Crack this paradox, and we might finally unite quantum mechanics and gravity, unlocking the universe's deepest operating system. Fail, and we're left with a reality where the past isn't just hard to read, it's been permanently redacted. Either way, black holes aren't just testing the laws of physics. They're asking us what reality really means when even the universe's trash bin comes with an undo button. If superposition and entanglement weren't baffling enough, the quantum eraser experiment takes the cake, a mind-bending demonstration where the present seems to rewrite the past. Picture this: you shoot photons one by one through a double-slit setup, creating that familiar interference pattern that proves their wave-like nature. But here's the twist: you add a detector to figure out which slit each photon passes through. Instantly, the interference vanishes as if the photons, now caught red-handed, switch to acting like particles. So far, so standard, but what if you wait until after the photons have already gone through the slits, when they're already in flight, to decide whether or not to peek at their paths? Astonishingly, the results change retroactively. It's as if the photons knew whether they'd be observed later and adjusted their earlier behavior accordingly. This isn't time travel in the sci-fi sense. Instead, it reveals a universe where quantum events remain unsettled until the full context of observation is complete. In delayed choice versions of the experiment, physicists use beam splitters and mirrors to erase the which path information after the particles have already traveled through the apparatus. When this information is erased, the interference pattern magically reappears, as if the particles were waves all along. But if the which path data is preserved, the pattern stays gone. The kicker: the decision to erase or preserve the information can be made after the particles have already hit the detector. Somehow, the present choice reaches back and reshapes what the particles did in the past. What's really going on? The key lies in quantum superposition's fluidity. Until a measurement locks in a particle state, it exists as a haze of possibilities. The past isn't fixed until the experiment's entire sequence, including later choices, is accounted for. Think of it like editing a movie after filming. If you cut a scene where a character picks a red shirt, you can later decide whether to leave that choice ambiguous superposition or confirm it collapsed state. The quantum eraser shows that reality, at its core, is more like raw footage than a finished film, malleable until the final edit of observation is complete. Practical implications are already emerging. Quantum cryptography exploits this retroactivity to create communication channels where eavesdropping leaves detectable scars in the data's past. Future quantum networks might use delayed choice protocols to optimize signal paths dynamically, rerouting information based on conditions that didn't exist when the signal was sent. And philosophically, the eraser blurs the line between cause and effect, suggesting that quantum reality isn't just strange, it's contextual, with the present and past co-creating each other in a dance we're only beginning to decode. So does this mean we can change history? Not in the way we typically imagine. You can't retroactively prevent a war or undo a mistake. But it does mean that at the quantum level, the universe refuses to commit to a single version of events until every possible observation is factored in. The past, it seems, is as fluid as the future, a notion that turns our classical intuitions inside out and leaves us staring into the quantum abyss, where time itself might just be another variable waiting to be measured. Imagine building a quantum computer so robust that even the messiest, noisiest environment couldn't disrupt its calculations. That's the promise of topological quantum computing, a radical approach that doesn't just fight decoherence. It sidesteps the problem entirely by encoding information in the very fabric of spacetime. At the heart of this revolution are particles so strange they don't even fit the standard categories of fermions or bosons. Meet ennions, the exotic quasi-particles that exist only in 2 dimensions and possess a mind-bending property. Their quantum states depend not just on their position, but on the intricate dance of their paths around one another. Picture 2 strands of spaghetti tangled together. The way they loop and twist holds meaning, independent of the noodles themselves. In topological quantum systems, information isn't stored in fragile individual qubits, but in the braided trajectories of these ennions, making it resilient to the microscopic chaos that plagues traditional quantum computers. Microsoft Station Q, a dedicated research lab founded by mathematician Michael Friedman, is banking on this approach to crack the scalability problem. While other quantum systems require near-absolute zero temperatures and painstaking error correction to maintain coherence, topological qubits could theoretically operate at higher temperatures and resist decoherence through their geometric structure. Here's why. In conventional quantum computing, a stray photon or vibration can flip a qubit state, corrupting calculations. But with ennions, the information is spread across their braided path. To disrupt it, you'd need to physically unbraid the particles, a feat so statistically unlikely it's like expecting a tornado to untie all the knots in a giant bowl of spaghetti without breaking a single strand. This inherent stability could finally unlock quantum computers powerful enough for real-world applications, from designing room temperature superconductors to simulating complex molecular interactions for drug discovery. The magic lies in topology, the mathematical study of shapes and their properties under continuous deformation. Unlike classical bits or standard qubits, which are vulnerable to tiny perturbations, topological qubits derive their stability from global properties that don't change under local tweaks. Think of it like a knot in a rope. You can wiggle the rope all you want, but the knot remains until you deliberately untie it. Ennions exploit this principle, with their braids acting as knots in quantum fields. Even if the particles jiggle due to thermal noise, the topological memory of their twists and loops stays intact. This isn't just theoretical. In 2020, researchers observed non-abelian ennions for the first time in graphene sheets cooled to near zero temperatures, marking a critical step toward practical topological quantum computing. Yet challenges remain. Ennions are notoriously finicky to create and control, requiring exotic materials like fractional quantum Hall systems or carefully engineered superconductors. Microsoft's approach focuses on Majorana zero modes, a type of ennion predicted to exist at the ends of nanowires. Early experiments reported promising signs of these particles, though debates about reproducibility linger. Even if the hardware hurdles are cleared, programming a topological quantum computer would demand entirely new algorithms tailored to braiding operations, a far cry from the gate-based logic of today's prototypes. The payoff, though, could redefine technology. A fault-tolerant topological quantum computer wouldn't just be faster, it'd be fundamentally more reliable, capable of running calculations for days or weeks without succumbing to errors. For industries like pharmaceuticals or materials science, where simulating quantum interactions could take classical supercomputers millennia, this could compress timelines to hours. And in cryptography, topological systems might offer unhackable networks, where information is shielded not by math but by the immutable laws of topology itself. What makes this quirk so thrilling isn't just its technical potential, it's how it forces us to rethink the nature of information. In a topological quantum universe, data isn't something you store, It's something you weave into the structure of reality, as enduring as the knots in an ancient sailor's rope. And that's a vision even Schrödinger's cat couldn't have imagined. If the quantum world thrives on uncertainty, the multiverse theory takes that idea to its ultimate extreme, suggesting that every possible outcome doesn't just exist in theory, but plays out somewhere in a sprawling, infinite tapestry of parallel realities. Picture a cosmic library where every choice you've ever made, and every one you didn't fills its own volume, each telling a different story of your life. This isn't just speculative fiction. It's a direct consequence of the many worlds interpretation of quantum mechanics, where every quantum decision point, every particle's spin, every atom's decay, splits the universe into branches, each carrying forward a different version of events. Consider Schrödinger's cat once more. In the Copenhagen interpretation, the cat's fate resolves into life or death upon observation. But many worlds argues there's no collapse, just two diverging timelines, one with a purring cat, another with a tragic ending. Now scale this up. Every breath you take, every glance at your phone, every decision to turn left instead of right could be spawning new universes, each humming along with its own unique history. The implications are staggering. Somewhere out there, a version of you skipped watching this video and became an astronaut. Another version never existed at all, their timeline altered by a single quantum fluctuation in their parents' past. Critics dismiss the multiverse as untestable metaphysics, and they're not wrong by definition. These alternate realities lie beyond our observational reach. But the math behind many worlds is surprisingly elegant, avoiding the messy collapse postulate of other interpretations. It treats the wave function as a relentless branching tree with no special role for observers or measurements. And while we can't visit these parallel worlds, their existence could explain some of cosmology's deepest puzzles. For instance, the fine-tuning problem why our universe's constants seem perfectly calibrated for life might just be selection bias. If countless universes exist with different physical laws, we'd naturally find ourselves in one where life is possible, however improbable. The multiverse also reshapes how we think about identity. If infinite versions of you exist, are you really making choices, or just experiencing one thread of a predetermined tapestry? Philosophers call this quantum immortality, the idea that your subjective experience might always follow the branch where you survive, no matter how unlikely. It's a dizzying thought experiment. Play Russian roulette in a multiverse, and while most versions of you perish, one inevitably lives, forever convinced of their preternatural luck. Technologically, the multiverse inspires wild possibilities. Some theorists speculate that future quantum computers might harness parallel timelines, offloading computations to alternate realities. Others imagine civilizations advanced enough to communicate, or even travel between branches, though the energy required would dwarf anything in our physics playbook. For now, the multiverse remains a playground for the imagination, a reminder that reality might be far vaster, stranger, and more interconnected than we ever dreamed. So the next time you hesitate at a crossroads, wondering about the path not taken, take comfort, or perhaps vertigo, in knowing that somewhere, somehow, every version of that story is already being told. The quantum multiverse doesn't just expand our sense of space, it redefines what it means to exist, one branching decision at a time. In a world where hackers breach firewalls and encryption gets cracked overnight, quantum cryptography emerges as the ultimate guardian of secrets, a system where the very act of spying destroys the information being stolen. At its heart lies quantum key distribution, a method so secure it doesn't just resist hacking, it exposes it. Here's how it works. Two parties, let's call them Alice and Bob, share a cryptographic key not through vulnerable digital channels, but via entangled photons. Each photon's quantum state, its polarization or phase, acts as a bit of the key. But here's the catch: thanks to the no-cloning theorem, it's impossible to copy these quantum states without altering them. Any eavesdropper, say Eve, trying to intercept the key would inevitably disturb the photon's delicate entanglement, causing errors Alice and Bob can instantly detect. It's like sealing a letter with a quantum wax stamp. If someone tries to open it, the stamp shatters, leaving undeniable evidence of tampering. This isn't theoretical. China's Cheshire satellite, launched in 2016, demonstrated quantum key distribution across continents, beaming entangled photons between ground stations over 1,200 kilometers apart. The result, a shared key secured by the laws of physics, not just math. Banks in Austria and Switzerland have already adopted quantum encrypted networks to protect financial transactions, while governments are racing to deploy similar systems for classified communications. The urgency is clear. With quantum computers on the horizon, traditional encryption like RSA could crumble in minutes under their brute force power. Quantum cryptography, though, remains unshakable. Even a future quantum supercomputer can't crack a key that self-destructs under scrutiny. But the magic isn't just in the entanglement. Protocols like BB84, named after its inventors Bennett and Brassard, exploit another quantum quirk: wave-particle duality. Alice sends photons polarized at random angles, vertical, horizontal, or diagonal. Bob measures them using randomly chosen filters. Only when they compare notes afterward, discarding mismatched measurements, do they distill a flawless secret key. Any interference from Eve would introduce anomalies, like a pianist hitting wrong notes in a silent room. The beauty: this doesn't just secure messages today, it future-proofs them. Even if Eve records the quantum transmission and waits decades for better technology, the laws of quantum mechanics guarantee she'll never decode the key. Yet challenges linger. Quantum signals degrade over long distances in fiber optic cables, requiring trusted nodes or satellites to bridge gaps. And while the keys are unhackable, human error in implementation can still create vulnerabilities, like leaving a vault door open despite an unbreakable lock. Researchers are tackling these hurdles with quantum repeaters, devices that extend entanglement's reach without breaking its security, and hybrid systems that blend quantum and classical encryption for practicality. The implications stretch beyond spies and stock markets. Imagine medical records shared between hospitals with zero breach risk, or voting systems where tampering is physically impossible. Quantum cryptography doesn't just upgrade security, it redefines trust in the digital age, anchoring it not in clever algorithms, but in the universe's immutable laws. So the next time you send a private message, consider this. The future of secrecy might not lie in harder puzzles to solve, but in codes that vanish the moment a stranger tries to peek. And that's a quirk even the most cunning hacker can't outsmart. Chaos theory taught us that a butterfly flapping its wings in Brazil could set off a tornado in Texas, but what if the butterfly's wings were quantum particles? The quantum butterfly effect takes this iconic idea and shrinks it down to subatomic scales, where tiny, random fluctuations might ripple outward with cosmic consequences. Imagine a single electron deciding to spin left instead of right. In our everyday world, that's negligible. No tornadoes here, but given enough time and the right conditions, that microscopic wobble could cascade through a system, growing exponentially until it alters the path of a comet, the collapse of a star, or even the evolution of life itself. This isn't just poetic speculation. Quantum chaos reveals how unpredictability lurks at every scale of the universe. Take something as mundane as a gas molecule bouncing around a container. Classically, if you knew its exact position and speed, you could predict its path forever, but quantum mechanics injects uncertainty into that trajectory. Heisenberg's principle ensures you can never pin down both the molecule's position and momentum perfectly, and those tiny errors snowball. Over millions of collisions, the molecule's path diverges wildly from any classical prediction, like a snowball rolling downhill that somehow ends up in orbit. Now zoom out. The early universe was a seething quantum foam, where fluctuations in energy and density were the rule, not the exception. Today's vast cosmic web, galaxies clustered along invisible filaments, might trace its origins to those quantum ripples stretched across billions of light years by inflation. It's a staggering thought. The Milky Way's spiral arms, the voids between superclusters, even the distribution of life-friendly planets could all stem from subatomic jitters frozen into spacetime during the Big Bang's first trillionth of a second. But here's where it gets wilder. Some physicists argue that quantum randomness isn't just a starting condition, it's an ongoing architect of reality. Consider DNA mutations, the raw material of evolution. Most are caused by quantum tunneling, where protons hop between molecules in a way no classical physics could predict. A single tunneling event could alter a base pair, leading to a new trait, a new species, or an extinction. In this light, life isn't just subject to quantum mechanics, it's a testament to its creative chaos. The quantum butterfly effect also redefines time's arrow. Chaos theory suggests that even deterministic systems become unpredictable over time, but quantum mechanics goes further, asserting that unpredictability is baked into reality from the outset. This raises a haunting question. If the universe's fate hinges on quantum dice rolls, does free will exist, or are we just along for the ride? Some interpretations say both can be true, that every quantum decision spawns branching timelines where all possible outcomes play out. In that view, the butterfly doesn't cause the tornado. It spawns a multiverse of tornadoes and calm skies, each equally real. Practical applications are already emerging. Quantum chaos informs everything from superconducting materials to fusion research, where controlling microscopic instabilities could mean the difference between a sustainable star in a jar and a fizzle. Meanwhile, quantum computers leverage chaotic effects to explore vast solution spaces, turning the butterfly's wings into computational power. Yet the grandest implication might be philosophical. If quantum fluctuations shape galaxies and biology alike, then randomness isn't just noise, it's the universe's way of exploring possibilities. From the spin of an electron to the spin of a galaxy, chaos and quantum mechanics whisper the same lesson. The cosmos thrives on uncertainty, and in that messy, unpredictable dance, everything from atoms to destinies finds its form. What if your thoughts aren't just electrical sparks flickering through neural networks, but something far stranger, quantum whispers dancing in the fabric of your brain? The quantum mind hypothesis dares to suggest that consciousness isn't merely the sum of firing neurons, but a symphony of subatomic processes playing out in the tiniest structures inside your cells. At the heart of this radical idea are microtubules, hollow protein tubes that form the skeleton of neurons, where some scientists believe quantum effects could be orchestrating the very essence of awareness. The theory, championed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, hinges on a provocative claim: classical physics can't fully explain the unity and richness of subjective experience. Think about the difference between watching a sunset and a camera recording one. Both process light and color, but only one feels the warmth, the awe, the fleeting beauty. Where does that inner experience come from? Penrose and Hameroff argue that microtubules, tiny cylindrical structures inside brain cells, might host quantum vibrations that collapse into conscious moments. These vibrations, dubbed orchestrated objective reductions, would bridge the gap between quantum weirdness and the seamless flow of thought. Critics are quick to point out the hurdles. The brain is warm, wet, and noisy, a hostile environment for delicate quantum states that typically require near absolute zero temperatures to avoid decoherence. Yet proponents counter with surprising evidence. Anesthesia, which selectively shuts off consciousness without stopping neural activity, seems to target microtubules, quieting their vibrations. Some studies even suggest that microtubules can sustain quantum coherence in biological conditions, thanks to their ordered structure and shielding by proteins. Imagine a bustling city where one quiet alley remains miraculously undisturbed, a sheltered pocket where quantum processes could persist long enough to matter. If true, the implications would rewrite not just neuroscience, but our understanding of existence itself. It could mean consciousness is a fundamental feature of the universe, woven into the fabric of reality at the quantum level. This isn't just about human minds, it hints that some form of proto-consciousness might exist everywhere, from the synapses of a mouse to the quarks inside a star. Some researchers speculate that near-death experiences or the elusive, hard problem of consciousness might find answers in these quantum vibrations, where the boundary between mind and matter blurs entirely. Skeptics remain unconvinced, arguing that classical computations in neural networks suffice to explain awareness. But the quantum brain hypothesis refuses to fade, fueled by mysteries like the speed of intuition, how we sometimes arrive at answers before logic could thread its way through our neurons. Could quantum tunneling or entanglement be shortcutting classical pathways, allowing flashes of insight that feel more like revelation than calculation? Whether the theory holds or collapses under scrutiny, it forces us to confront a profound question. Is consciousness a mere accident of biology, or something deeper, stranger, and more entangled with the universe's fundamental nature? The answer might lie not in the synapses alone, but in the quantum shadows flickering between them, where the mind, just maybe, meets the cosmos. What if everything around us, the stars, your morning coffee, even the ache in your knees when it rains, isn't fundamentally real, but an unfathomably detailed simulation running on some cosmic quantum computer? The simulation hypothesis, once relegated to sci-fi, has clawed its way into serious scientific discourse, fueled by eerie parallels between how our universe operates and how a hyper-advanced virtual reality might function. Think about it. Quantum mechanics already shows us that particles exist in fuzzy superpositions until measured, like a video game rendering graphics only where the player looks. Entanglement's instant correlations mirror optimized code that skips calculating separate objects when they're not being observed. Even the Planck length, the smallest possible unit of space, hints at a pixelated universe, a cosmic resolution limit preventing infinite subdivision, just like a digital simulation avoids infinite memory usage. Philosopher Nick Bostrom formalized the argument in 2003 with a trilemma. Either civilizations like ours almost always go extinct before reaching post-human status, they lose interest in creating ancestor simulations, or we're almost certainly living in one. The math is chilling. If even one advanced civilization avoids extinction and runs countless simulations of their ancestors, the number of simulated minds would dwarf biological ones, making it statistically likely you're one of them. Elon Musk famously quipped the odds are 1 billion to 1 we're in base reality, but physicists approach the idea differently, probing for glitches in the matrix. Some suggest testing whether the universe operates with finite computational resources, like searching for signs of energy saving rounding errors in high-energy particle collisions. Others propose hunting for evidence the cosmos runs on quantum circuits, where spacetime itself emerges from entangled qubits, a notion that dovetails with holographic principle research. Yet the hypothesis isn't without skeptics. Nobel laureate Frank Wilczek argues that inventing an unseen simulator explains nothing. It just kicks the can down the road to who created them. Some quantum theorists point out that simulating every particle in the universe would require more energy than the universe contains, though counterarguments suggest the simulation might cheat, rendering only observed phenomena in detail, like a video game's fog of war. Ironically, our pursuit of quantum computers, machines leveraging superposition to simulate nature, might one day provide the tools to test whether we're inside one. If we eventually build simulations indistinguishable from reality, the statistical case for being in one ourselves becomes overwhelming. Beyond physics, the simulation hypothesis reshapes existential questions. If reality is programmed, do free will and meaning evaporate, or does the coder's intent imbue them with new significance? Could glitches explain déjà vu or UFO sightings? And if the simulators exist, are they themselves simulations in an infinite regression? Whether terrifying or exhilarating, the idea forces us to confront that the universe's deepest quirks might not be bugs. They could be features carefully coded into the fabric of everything. And that's the ultimate quantum quirk, the possibility that our thirst for understanding reality might one day reveal it's not even there. From superposition to quantum teleportation, these 28 quirks reveal a universe that constantly defies our expectations, where particles vanish and reappear like cosmic magicians, where cats can be alive and dead, and where the simple act of looking changes what's being seen. What started as a scientific revolution to explain the behavior of atoms has blossomed into a radical rethinking of reality itself. Quantum mechanics isn't just a tool for physicists, it's a lens that reshapes everything from technology to philosophy, proving that the fabric of existence is far stranger, far more dynamic than our everyday experiences suggest. Consider how these ideas ripple outward. Quantum entanglement isn't just a laboratory curiosity, it's the foundation of unhackable communication networks, linking satellites and ground stations across continents. Superposition isn't just a thought experiment. It powers quantum computers that could one day crack problems no classical machine could solve in a lifetime. Even the bizarre quantum tunneling, once dismissed as an oddity, now explains everything from nuclear fusion in stars to the flash memory in your smartphone. The line between abstract theory and tangible impact blurs when you realize these quirks aren't just quirks, they're the hidden scaffolding of our world. But the implications run deeper than gadgets and equations. Quantum mechanics forces us to confront profound questions about the nature of reality. Is the moon really there when no one's looking, or does it hover in a haze of probabilities until observed? Does consciousness play a role in shaping the universe, or is measurement just another physical interaction? The answers, or lack thereof, challenge our most basic assumptions about objectivity, causality, and even free will. It's no wonder Einstein struggled with these ideas, calling entanglement spooky and insisting that God does not play dice. Yet decades of experiments keep confirming the dice are indeed rolling, and the universe seems perfectly comfortable with the chaos. What makes quantum mechanics so endlessly fascinating isn't just the science, it's the way it humbles us. For all our intelligence and technology, the cosmos retains mysteries that defy intuition, reminding us that reality is under no obligation to make sense to human minds. Every time we think we've grasped the rules, the quantum world throws another curveball: time crystals that never settle. particles that separate from their own properties, or simulations so convincing we might be living inside one. The more we learn, the clearer it becomes we're just scratching the surface of something vast and incomprehensible. So as we wrap up this journey through the quantum landscape, here's the real takeaway: curiosity is our greatest tool. Whether you're mesmerized by Schrödinger's cat, baffled by the holographic principle, or still reeling from the delayed choice quantum eraser, these ideas invite us all to marvel, question, and explore. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's the most thrilling part. Now it's your turn. Which quantum quirk left you awestruck? Drop your favorite in the comments, and if you've enjoyed this dive into the subatomic unknown, hit subscribe to join us for more mind-expanding adventures. Until next time, keep looking deeper, because reality, it turns out, is always one step ahead.